Of course, I wasn't recording any of that, but so I'm going to start again. We're going to do scientific engineering notation and then talk about binary numbers and hexadecimal numbers. Okay, and probably the last, like the engineering notation, the binary and the hexadecimal are probably new things to you. So you might want to rewatch the video if you need to. You'll notice that, and my math lab has a 1.5 section, which is our scientific and engineering notation. You'll see a homework assignment for that. The binary and hexadecimal does not have an assignment in my math lab. I have it as a paper assignment. So I'll show you at the end what I want you to do to submit that. And if we have extra time at the end of class, I'll let you actually spend some time doing it. Okay, do I have any questions on anything before I start in? Are good? All right. If you notice that someone's waiting to get in, let me know. Sometimes they'll text you. You can just jump in and let me know. That happened the other day, my 1 o'clock class. I didn't catch them because of my screen sharing. I can't see that they want to come in. Okay. So we are on slide, it seems like 45. Okay, scientific notation, you probably have been exposed to it either in grade school or in high school or in a science class, because we use it to represent large numbers and small numbers, and it helps us in science, in science classes when we're talking about large numbers like the distance from here to, to the moon, or the speed of light or something, or when we're talking about something really small like the diameter of a nucleus or something, or a cell. So we wouldn't want to be working with all those really small numbers or really large numbers with all the extra zeros that we see. So a number in scientific notation is expressed in the form a times 10 to the k, where a is a number between 1 and 10. A can be 1. It'll have to be greater than, here, sorry, marking here. Morning, Pat. Were you kicked out? Or I already knew he was coming or something because Pat's in there, but I gotta get back in. Okay, so A is a number between 1 and 10. It can be 1, not including 10. And K is an integer. Oops. Okay, remember integers are those numbers that are -2, -1, 0, 1, 2, and so forth. Okay, so let's do some examples of scientific notation. So the speed of light is approximately 186,000 miles per second. So if I wanted to convert this to scientific notation, I have to first locate the decimal place, which is right here. And now I need to make my a number between 1 and 10. So I need to move the decimal place to a place, oops, we're just going to do that when I hold it, 1, 2, 3, 4, 5, that will create a number that's between 1 and 10. So I'd have to move my decimal place in between the 1 and the 8 to do that. So 1.86. Now we're keeping significant digits here. So those extra zeros are not significant right now. They're placeholders, and that's going to help us with our K value. So I've made the number 1.86. Then I got to do 10 times 10 to the count the number of decimal places that we moved, which was 1, 2, 3, 4, 5, and that is our K value. All right, so moving on to the next example. The diameter of a typical individual fiber in a fiber optic communications cable is approximately 0.000005 meters. That's really small. And so we're going to write that in scientific notation as well. So I'm now I have a small number. So I'm using negative exponents when I am talking about small numbers. I used a positive exponent up here when I talked about very large numbers. I mean, this isn't very large, but it's larger than 1. So when I have a number smaller than 1, I'm using negative exponents. It does not mean a negative number. It means really small. So I think I said 1, 2, 3, 4, 5, 6, and I'm not sure I counted them before, but I'd have to move the decimal place 6 places. 1, 2, 3, 4, 5, 6. So I can make that A value a number between 1 and 10. I don't want to make it 0.5 because I need the number greater than 1 or equal to 1. So it would be 5 times 10 to the, we moved it to the right 6 places. So it's going to be negative 6 times 10 to the negative 6. Okay, what this really is saying is that 1.86 is times, well, 10 to the 5th is like a 1 with 5 zeros. It's 10,000. Oh, it is not 10,000. It's 100,000. I need 5 zeros. So that was silly of me. I'm going to put 4 zeros on that. It's 5 zeros. It's 100,000. Get a little nicer. Okay, so if I multiplied 1.86 times 100,000, because that's what 10 to the 5th is, I would get 186,000. So but we don't want to write all those zeros either. So we're writing it as 10 to the 5th power. Same thing down here, same idea here. You're talking about 5 times 10 to the negative 6. This is your answer here. Don't get confused by my extra work. I was just showing you where it's coming from. So 5 times, you're talking about, wow, 1.1.00005 times this number here. This is 10 to the negative 6. That number is 10 to the negative 6. I don't know if you can see it. Probably have it really tiny, especially if you're using a cell phone. 4, 5, 6. And when you multiplied that by 5, you would get this number here. So I'm not asking you to write all those zeros out. I just wanted you to see what those meant. Make sure okay. But this is our answer. That makes it easier. Now I am missing something on my numbers in both of these examples. What am I missing?
Like the MIS and meters.
Yeah. So this is going to happen to me from time to time. Is I'm going to accidentally leave off my units. It's not I mean, I shouldn't, I can't. So you got to keep me honest up here. So this is miles per second and then meters. Next. All right, so to change a number in standard, or what we would say ordinary notation, to scientific notation, A times 10 to the K. A is a number between 1 and 10, and K is an integer. We need to move the decimal point so that only one non-zero digit is to the left of it, and that digit is A. The number of places the decimal point was moved is K, which is the power of 10. So if the decimal point is moved to the left, then K is a positive integer. So let's do an example of 80,000. If I did 80,000, I'd have to move the decimal place 4 places to the left. 2, 3, 4. So it had 8 times 10 to the 4th. In that case, I have an example of 8,150,000. So moving the decimal place since it appears right after the 0, I'd have to be 1, 2, 3, 4, 5, 6. So I'd have 8.15, keeping all the significant digits, times 10 to the 6. And you can move your decimal place. It might be easier instead of counting 1, 2, 3. You can count by threes, like here's 3, here's 6, and move it 6 places to the left. So it's a positive K value. If the decimal point is moved to the right, then the K is a negative integer. Our example here, I have 0.00075. So I'd have to move the decimal place 1, 2, 3, 4. So I'd have 7.5 times 10 to the negative 4. And we want to write our number in the form where we have an a value times 10 to the k. And k is the integer. All right, so why do we do this? Well, it helps us speed up some work. It makes, you know, when you're talking millions and billions, there's a lot of zeros, a lot of decimal places, you know, a lot of places there. Not decimal places, but and then when really small numbers, we have a lot of decimal places. So it makes it hard to type in the calculator as well. I mean, you can do it, but you can miss a zero. But it makes computations by hand faster, almost as fast as using the calculator, or at least simplifying. So if you're trying to do the division here between these two numbers, the number 0.00018 divided by, this is thousands, millions, billions, so 1,200,000,000. Those are big numbers. We could write it in scientific notation and we won't need our calculator. So without our calculator, let's attempt this problem. So on the top, I'm going to write both of these numbers in a scientific notation. So on the top, moving the decimal place to the right is going to give me a negative exponent, 1, 2, 3, 4. So I have 1.8 times 10 to the negative 4. My denominator, well, I know I'm going to move it 3, 6, 9. So I have 10 to the 9th, and the number is going to be 1.2. Okay, so now I can do the math here. So I can split this up. And 1.8 divided by 1.2, you still don't need your calculator. Hold off on that. Times 10 to the negative 4th all over 10 to the 9th, like this. Okay. So when you have decimals in a fraction, you can multiply the top and the bottom by 10. So you could write this as 18 over 12 times 10 to the negative 4. Well, what's 18 divided by 12? Well, 6 goes into both of those. 6 goes into 12 twice. 6 goes into 18 3 times. So we have 3 halves. 3 halves is a decimal. Well, that's 1.5 is 1.5. And then times 10. Well, here, the 10 to the negative 4th over 10 to the 9th, we can do this using our properties for exponents. They have like bases, right? 10 is the like base. When you're dividing like bases, you subtract their exponents. So a negative 4 minus 9 would give me 10 to what power?
Negative 13.
Mm-hmm. And there you are. So we have one, if you can't read this, I'll read it out loud again. It's 1.5 times 10 to the negative 13. It's much better than writing it in standard notation, and it's easier than even pulling out the calculator. And I showed way more work than you probably need to show. Maybe you do if you're kind of not used to it, but that you could probably show less work and still get the right final answer. Okay, let's do another example. So Coulomb's law is a law of physics describing the electrostatic interaction between electrically charged particles. I'm not asking you to understand that or even know this law, but you can find that there's variables in there and you can plug. So that's the beauty. Like you are going to be applying your math in whatever way that you know, whatever field you choose in this tech field, or if you're into engineering of some sort. So you're going to, you know, use different laws than what even, you know, another field would use. So you just got to be careful with your units. You have to make sure you know the properties of exponents, how to multiply, divide, add, subtract, all that good stuff, and be able to plug in with variables. And here we are. So we've got F, and you'll see, and that's the electrical force between two charged particles. And you have K. Don't worry about it. It's the constant of proportionality. And then you have Q sub 1 and Q sub 2 inside of absolute values. So you need them to be positive. You're going to multiply them, and then you're going to divide by R squared, R being the distance between the objects. So you're going to square that. So just follow your order of operations. So I want you to find F. I want you to find what this is, given what Q sub 1 is, what Q sub 2 is, what R is, and what K is. You're going to have to write small. I had to write really, really tiny. So I'm going to try my very, very best to write tiny on the slide, but I need every square inch of it. Let's see here. Keeping units in your problem. going to try to get rid of the, all right, so we're going to find F. So we have to replace K. K we know as 9 times 10 to the 9th newtons times meters squared all over C squared. So leave all of those units with it. So K, 9 times 10 to the 9th newtons times meters squared C squared. And then we have our fraction. We're going to multiply this by the absolute value of Q sub 1. Q sub 1 is 1.0 times 10 to the negative 10. That is positive. I don't really need the absolute values, but I'm going to leave them in there for now. I'll get rid of it in a little bit. I'm going to multiply that by Q sub 2. Do I have my units on that? I forgot my units at the end of that. I think it was C. Right, the unit was C. And then times, we have negative 2.0 times 10 to the negative 9. C. All right, this number is negative. We will make it positive before we multiply. And then R squared. So 0 to M for R, so meters squared. All right, so 9 times 10 to the 9th newtons meters squared C squared times, now in the numerator I'm going to drop, I need to take the absolute values of these two numbers. We talked about this one is already positive and this one was negative, so it will have to be positive. So it's going to be 1.0 times 10 to the negative 10C times negative 2.0 times 10 to the negative 9C all over, oh boy, that's not a very straight line, squaring 0.02 and squaring the M, you got to square the units as well. So 0.02 times 0.02, that's 0.0004 meters squared, okay? You still with me? Okay, no. Does somebody want me to back up and show something else?
Just a little fast.
Okay, I'll slow down. I get excited. So, and I can't really see most of you, unfortunately. I can see you, Don, so that's good. So I know if it's going, so I'll let you copy this down. Okay, is that, are you caught up or another second? Give me a thumbs up or a wave when you're done. Okay. At this point, you might grab new paper anyway. Thanks, Dan. Don, you good, or do you need me to read something so you can see it?
I'm good.
Okay. So now I'm going to maybe, I guess I'll wait a little bit longer before I cancel units. All right, so I have 9 times 10 to the 9th Newton meter squared all over C squared. And then this fraction here, I'm going to go ahead and multiply this numerator. So when I'm multiplying the 1.0 times 10 to the negative 10. That's the units. So we'll multiply that by the units over here. And then I'm still multiplying this times, now this is a positive. See, I went too fast. I should have caught myself. When I went from the absolute value, I dropped the absolute values and now a positive 2.0. See, good thing we went back carefully. All right, so I'm multiplying this times this times this times this, those four together. Now what I'll do is something convenient. I'm going to multiply the 1.0 times the 2.0. Well, 1 times 2 is 2. Times, what do I have? Okay, yep, I got it. Times 10 to the, now I'm going to take the 10 to the negative 10 power times 10 to the negative 9 power. So I'm just going to come over here for a second. So 10 to the negative 10 power times 10 to the negative 9 power. When you're multiplying like bases, you add their exponents. So a negative 10 minus 9, negative 19. Okay, so I'd multiplied this times this. I multiplied the 10, the base 10s, and now I'm going to multiply the c times c. Those are units, so we're just going to put c squared. You multiply c times c, you get c squared. My denominator, I can't really do anything more with it right now, so I'm just going to bring it down. All right, now let me cancel some units. Start simplifying some of those because they're getting kind of in the way, a little messy. But they're necessary because and the beautiful thing about keeping units in your math problem is the units multiply, divide, add, and you know, just like we do with our numbers or any of our like what you do with variables, I should say, not numbers. So the c square can cancel with this c square. This is in the numerator, this is in the denominator. You can cancel those two units. We can do the same thing with the meter squared. There's a meter squared in the numerator and there's a meter squared in the denominator. And I'm multiplying these together so I can cancel those. Okay. So my final answer, the units are going to be in newtons. It's the only unit that I wasn't able to cancel. So that I'm going to put towards the end in the next step. So I'll wait to put the n in the final answer, okay? So let's take, again, looking to see the operations we're doing. We're multiplying 9 times 10 to the 9th times 2 times 10 to the negative 19. So that's all going on in the numerator, and then the n is going to go out at the end. You can treat this all over 1 if it makes you feel better. You can have an over 1, so you can see that you're multiplying this fraction times this fraction, up to you. All right, so I'll do what I did up here where I took the coefficients. So the 9 times the 2, I'll get 18, and then times, now we have 10 to the 9th times 10 to the negative 19. So 10 to the 9th times 10 to the negative 19. When you multiply like bases, you add their exponents. So you'll have 10 to the negative 10. So then we have in the denominator, we have our 0.0004. I'm going to write that in scientific notation, so it's going to be easier for us to simplify with this up here. So this would be 4 times 10 to the, how many places I'm moving that decimal place would be 1, 2, 3, 4. And it's moving it to the right, so it's a negative exponent. And if I don't remember if I'm moving it left or right, it's a small number, so you're putting a negative exponent. And if it's a large number, you're using a positive exponent. Okay, so then now I can simplify this. I still got that n. I got it kind of way out there. I'll move a little closer. All right, so then I can now simplify these two numbers, 18 divided by 4. Well, 2 goes into both of those. So 2 goes into 4 twice. 2 goes into 18 9 times. And 9 over 2, although I don't always love decimals, but decimals are appropriate here. 9 over 2 is 4.5, or 4.5. Times 10 to the, now we got to figure out what happens here. When I'm dividing, I'm going to come over, I'm going to come up to this, I'm going to use this space over here. So you have 10 to the negative 10 divided by 10 to the negative 4. Oh, I'm sorry about that, guys. Gals, go this way. when you're dividing like bases, you're subtracting their exponents. So a -10 minus a -4. So that's like +4. So you get 10 to the -10 plus 4 would be -6. Okay, and then the last thing I need to do is put on my units. Okay, before I finish, we had to do some math here. Sometimes this number, when I'm dividing like 18 by 4 or 9 by 2 or whatever I divided, because I simplified it before I divided, so I didn't have to use my calculator at all. I didn't pull my calculator out once for this problem. This number sometimes turns out to not be a number between 1 and 10. So sometimes you then have to adjust a little bit more with your final answer. But we were lucky this did come out to be between 1 and 10. Okay, was the speed okay on the end? Okay, a couple of acknowledgements. All right, thanks. So you'll practice some more with scientific notation. The rules haven't changed since you learned it your first time. So you just probably need a little more practice or take your time. I have to also take my time. So talking about another notation will be engineering notation. And this might be relatively new. I'm not sure you've ever seen engineering notation before. So a number in engineering notation is expressed in the form a times 10 to the k, where a is either a number between 1 and 1,000, not 1 and 10 this time, but 1 and 1,000, and k is a multiple of 3. All right, so let's take a look at what multiples of 3's are. So a multiple of 3, you probably know, is 3, 6, 9, and so forth, continuing. But it's also, you could say 0. 0 times 3 is 0. 0 times a -1 would be -3, -6, so forth. So there's our pattern. And the question might be, why 3? Why are we using a multiple of 3? And it has to do with the metric system. So if you think about a meter and centimeter, there's 100 centimeters in 1 meter. So 100 is, we deal with powers of 10. You think about mega, you think about giga, you think about tera. I mean, those are all you can think about, all of them in triples, okay? So write each number in engineering notation, or kilometers. I should probably use 1 meter equals, being better, 1,000, nope. 1 kilometer equals 1,000 meters. One kilometer equals 1,000 meters. And 1,000 is 1 times 10 to the 3rd. Okay, so if I wanted to write this number, I want you to write in engineering notation. So if I'm writing 15,060,000 in engineering notation, I'm looking for groups of 3. I want the number between 1 and 1,000. So if I move my decimal place, here's 3. Here's another 3, because I can only do it by multiples of 3. I want to write the number 15.06 times 10 to the, 3 and 6. So our exponents here in engineering notation are going to be 3, 6, 9, or -3, -6, -9. We aren't going to have like 5 or 4 or 7. If this was in scientific notation, you would have moved the decimal place here and given yourself 1.506 times 10 to the 7th, but we don't want that for engineering. Engineering's in triples. Okay, so I can only move the decimal places by 3, so I'm going to move this decimal place here. So 1.4 times 10 to the -3. That scientific and engineering actually match in that case. Sometimes they will. They are the same. Okay, and then 520. Well, I can't move 3 because then I'd make a number that's smaller than 1. If I move my decimal place, which is here, 3, because I can only move by 3s. It's not gonna fit that A that has to be between 1 and 1,000. So 520 will stay 520, but it'll be times 10 to the 0 power. Anything to the 0 power is 1, so this is gonna be 520 times 1. But in engineering notation, you'd write this. Okay, now you won't have practice on this in my math lab, but you will see it on the exam. You go to take it. So you might want to note that you won't be practicing engineering notation, but you'll have it for, you'll see it on the exam. So you want to come back to this when you're taking your exam. Okay, so scientific and engineering notation on the calculator. So if you have your graphing calculator near you, does everyone have a graphing calculator? When I say that, everyone's going to say yes. So does anyone not have a graphing calculator yet? Night. Okay, so everyone seems to have one. Awesome. Did anyone borrow one from the library this semester? No? Okay. So in the calculator, when you hit mode, do you need me to show you mine, or someone needs me to show the calculator? Just say please, and tell me you want me to bring it up, and I will. Your mode, under the mode menu, you'll see this, and you're going to want to have highlighted this whole left side column. Now look here, you'll see that science and engineering notation do show up. So, I'm just going to get out my calculator, but I think I'm going to. Can you see? I don't know if you can see this or not. Maybe I'm just sharing the slides. I'm going to stop the share for a sec. Can you see the calculator? Okay, awesome. So in mode, I have a cool mode menu because I have the TI-84CE, so it graphs in color. I know you're all jealous. Or does somebody have the CE? Okay, yeah, isn't it sweet? I mean, it's worth it. I love it. I mean, worth it to a math person. I don't know that it's worth it if I already owned a TI-83, and I'd rather keep the $100, $150, but I still like it a lot. All right, so the scientific notation, to get over there, just arrow to the right and you can hit scientific. I can show you. Is someone talking? So let's practice with this number here. It's first gonna, take that number and find it in scientific notation using our calculator. We expect it to be 5.2 times 10 to the 5th. That's what I'm expecting, 5.2 times 10 to the 5th. So I've got to put my calculator in scientific notation. And I'm gonna 520,000. Hit enter, and look what I get. Okay, so it doesn't exactly say times 10 to the 5th. It says 5.2, and it has e to the 5th. So this we have to understand. So it's understood that that E means times 10 to the 5th. You know, this E to the 5th is telling you that, or E5 or whatever it's saying. Now let's do it in engineering. Same number. Let's get engineering. So type that number in again, 520,000. And I need to go to my mode first. I should have done that first. Switch it to engineering. Go back. So I'm gonna, to get out of this menu, I didn't mention this before, I kind of did it fast. To get out of this menu, you quit. So I'm doing second mode, which is the quit is right above it. All right, now I'm gonna hit enter. And I see this. Is that what we have? 520, because when you're doing engineering notation, you could have only moved the decimal place 3 places. If you moved it the next 3, it would have made a number smaller than 1. So we have 520 e to the 3rd. So then we can do thousands, millions, billions, and so forth using engineering notation. Okay, any questions on that? You know, and I never mentioned this the last class because sometimes, you know, I expected to only stay about an hour, hour and 15 minutes or something like that every class. And then one class, I don't know if it was your class or my 115 class, it went almost 2 hours, which, you know, is like a regular class. If you need to like take a break, just pause. I mean, you just turn off your camera or something and then, you know, come back in when you're ready. Feel free to do that. And then you can watch whatever you might have missed. But don't, I'm not going to be offended if you have to, like, you know, go take a break for a second. So binary and hexadecimal numbers, this is something probably, anyone ever worked in binary? I mean, you've heard of binary. Anyone work in binary before? Who are my computer people? Computer science, computer programming. Okay, so Dan, anybody else? I can't really see. Right. Okay, you too, Kieran. Yeah, nice. All right, awesome. And then hexadecimal, we'll talk about that too, okay? So we're changing, just to warm up before we start in here, these are 2 new base systems for us to work with. The number system we work with and use today on a regular basis is called the decimal system. And it's based on the powers of, who's got this? All of our digits, right? So 10. It's in the, it contains 10 digits. So the powers of 10, and it contains 10 digits. Those are related. All right, the 10 digits we have in our number system, I mean, with 0, 1, 2, so forth, all the way up to 9, right? We don't write 10 because 10 is 1 and 0. We have 10 digits. When we're back to 10, we use that 0 again, and then we're just moving, then we would be moving our places. So notice that the number of digits is the same as the base of the system. When we said based on those powers of 10, we have 10 digits. They are the same. So position of the digits is very important. We know this in our own math system, and we call it the place value. So I'm still in base 10 right now. I'm in our normal system that we use in you know, the US on a regular basis. And we have the number, I have 4857.21. You know that I cannot switch these digits. If I was to write this as 8475.12, they have the same digits, but this is not the same number. So not equal, I mean, you cannot do, you can't just swap digits. The place in which and where they show up is really determining the number and how big it is, how small it is. So we have to be very careful that we are paying attention to place value. And it's easy in our decimal system because we're so used to it. So we want to be able to keep that in mind as we move forward. So when you have a 1001, it's different than a 1100. You know, it looks like there's only 2 ones in there, but where they're placed is important. Okay, so binary numbers have a base of 2. And it's very helpful with computer programming. You hear that probably the most. And it's a sequence using the digits just 0 and 1. And this is a binary number that I have written right here for you. Usually in binary numbers, you might see them grouped in 4s. So you might see this number, I'll just draw a line here for a second, and you would see 1 0 0 1 there, and then you'd see space and you'd have a 1 1 0. But to keep it with a group of 4, we'll throw a 0 in front. It's just more visually pleasing, but it's not going to change the number by putting a 0 in front. Just like if I put 0 8, it's no different than 8 in our normal system, in our decimal system. So we can do that here as well, but we put them in groups of 4, and a group of 4 is called a nibble. And each one of these right here is a bit. And a bit comes from the word binary digit. So each of these is a bit. A group of 4 of these is a nibble. A group of 8 of this is a byte. We've heard of byte before. Okay, is nibble a new word? Not for Dan. Anyone else? Yeah. Byte, we've heard before, maybe didn't understand how it was found, but a nibble is usually a new word for people. Okay, so let's do some writing of binary numbers. Okay, a binary number is sometimes written with the subscript 2 when there is a chance that the binary number might be mistaken for a decimal or a base 10 number. So for instance, if I write the number 10, and you saw that any other time today, before this conversation today, you would have said that's number 10. So if we're talking base 2, you can see a number like 10, but it won't mean 10. So sometimes you'll see a little subscript that tells you this is base 10, so this means the number 10, and this means something completely different. This means 10 with a base of 2, and we'll discuss that. But most of the time, we do not have to write those subscripts. It's going to make sense in the context. So if we're not talking about binary, then I'm not writing a base 10 here. We don't ever do that on a regular number, so I'm not going to be throwing that on there. We might do this if we were talking about this, but I think the formatting of our binary numbers, you won't even need to show your little subscript. Okay, long binary numbers are often written with their bits separated in groups of 4 with a space in between, and commas are not used. So let me just put up an example here. Looking at a number like that, go ahead and write it down. Get all those zeros and all those ones correct. It's hard. If you look at it this close together like this, it's kind of like a credit card number. You write 16 digits right next to each other, it's hard to read it. So we group them in 4s. It's a little easier. So we start grouping in 4s just like we would if we were making groups of 3 when we do it in our own system, when we use commas. We would start from where the decimal point would be here. This is not a decimal point, it'd be a binary point. It still shows up at the end of the number. We still have a whole number here. So I'm going to put in lines to group them in groups of 4. Okay, starting from the right to the left. So you want to get this group of 4, this group of 4. Then this over here only has 2, so I can put in the extra zeros to give you the group of 4. And it will not change the value. So writing this with the spaces in between, it has 0 0 1 0 space, then this group of 4, 1 1 0 1, then the last group of 4, 0 0 1 1. All right, this is just easier to read. This isn't wrong up here. It's just a lot easier to read if we group it this way. Now this digit that shows up on the left is the most significant digit. And this number here is our least significant digit. Now, we would probably be, this 0 is just there as the placeholder, so this 0. So I'm just describing that on the left is where you're going to find your most significant digit, and it probably will be this 1 in this space. And I'm going to abbreviate them MSB and LSB. So you'll see me do that throughout when we're trying to convert our numbers. Okay. Before we actually start figuring out what these numbers are or converting them into the decimal system, let's kind of understand the base, what's going on with these powers of 2, powers of 10. So in our basic 10 or our decimal number system, we have our decimal point. It's kind of our place of reference. And then if we move to the left of the decimal place, we can describe these different place values. So you know right to the left is the ones place. So 10 to the 0, that's a 1. Any number to the 0 power is a 1. So this is the ones place. And then if we move to more to the left, it's going to give you the tens place. 10 to the first is 10. Then the hundreds place. 10 squared is 100. The thousands place. 10 cubed. And so forth. So as we move more to the left, further away from that decimal point on the left, we have a higher power of 10. And we would have whatever digit we had. So if we had the number, let's say 35,703, this is 3 times 10 to the 4th. This is 5 times 10 to the 3rd. This is 7 times 10 to the 2nd. This is 0 times 10 to the 1st, and then 3 times 10 to the 0. That's how, and we can write our number that way. Now with the base of 2, oh, and I didn't mention over here, so as we move to the left, our decimal places, as you see, we're decreasing. So we went from 0, then we go to -1. This is like 1/10, right? So this is the tenths place. This is 1 over 10 squared, or 100. So the hundredths place of the TH. The 1,000ths place, and so forth. So we don't have a ones place to the right side of the decimal. It's the tenths, hundredths, thousandths, and so forth. So base 2 or binary number system, here's our binary point. It's not called decimal point, it's a binary point. And right to the left, I shouldn't say right to the left, but next to it on the left, 2 to the 0 is 1. Then we have 2 to the first, 2 to the second, 2 to the third. So our powers of 2, our base of 2 now, our powers of 2 are increasing by 1 as we move to the left and decreasing by 1 as we move to the left. So then we have 2 to the -1. That's a -1 over 2. Not negative, sorry. 1/2, 1 over 2. 1 over 2 squared, which is 4. 1 over 4. 1/4. This is going to be 1 over 2 cubed. That'll be 1/8, and so forth. Positive. These are just going to be small. They're going to be decimal, you know, smaller numbers as we're converting over. Okay. So expanded notation. A number in expanded notation is expressed as the sum of the products of each digit and its place value. So I started an example on the last slide and I didn't continue it, but I started it with that 35,703. I was saying it out loud, but let's actually write it down. So a decimal with a base 10 number of 8,156, let's express it in expanded notation. So let's take it and write it down here, 8,156. And I'm going to take a look at its places. So the digit 8 is in the, this is the ones place, tens, hundreds, thousands place. So it'd be 8 times 10 to the third. That's the thousands. Remember, this is 10 to the 0, 10 to the 1, 10 squared, 10 cubed. We're going to add it to 1 times 10 to the second. And that tells us that we have 1 times 100, right? That's 100. Well, that's 100. This 1 here means 100. Then plus the 5 times 10 to the first, plus the 6 times 10 to the 0. Give you a second to catch up with writing that down. So this would be 8 times 10 to the third is 1,000, plus 1 times 10 to the second, this is 100, so it'd be plus 1 times 10 to, no, 1 times, not 10, 1 times 100, plus 5 times 10, plus 6 times, well, 10 to the 0 power is 1. So simplifying this, 8 times 1,000 is 8,000. Plus 1 times 100 is 100, plus 5 times 10 is 50, plus 6 times 1 is 6. So that would be expanded notation. Okay, that helps us establish how we do the binary. So although that should have been rather straightforward, this will help us with the binary. So we started, this digit was 10 to the 0, 10 to the first, 10 to the second, 10 to the third. As we come down here, this is my binary number. I have 1, 1, 0, 0, 1. Okay, this digit, I'll start from the most significant, but this is 2 to the 0, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. So this 0 on the left is going to be 1 times 2 to the fourth, plus, now this digit here, 2 in, be 1 times 10 to the third, plus, now the zeros I don't have to write because 0 times the number is going to be 0, but I'll put it there just for our first example. So 0 times 2 to the second, plus 0, the 0 here, times 2 to the first, plus this last one times 2 to the 0 power. What's 2 to the fourth?
16.
Mm-hmm. What's 2 to the third?
8.
Mm-hmm. 2 to the fourth? 2 to the second? 4? 2 to the first, okay? So this, I'm going to leave it at this. This is our expanded notation for binary. This is what it's saying. Okay, we can add it. I can add this. We have 16 plus 8 plus 4 plus 2 plus, we said 1. But this is going to be what we would consider in decimal. I would be adding these, and this would give me the decimal number. Decimal notation. Oh, shoot, this is so close to mine. So what is that? 24, 28, 30, 31? That's the number 31. Did I add right?
Wouldn't the 4 and 2 be non-existent because it's time?
Oh, yes.
Timesing by 0.
I'm going too fast. Yep. Thank you. Thank you, thank you. I'm going to do this too often here, and I don't mean to. I get so distracted with all our jumping back and forth. So yes, 0 times 4 is 0. I think I mentioned that before, and then I just wrote it down as 4 anyway, and then because I was so concerned about the 2 to the first and 2 to the second, this would be 0 as well. So are we, I think we're looking at 25 then. Oh my God. that just zoom like huge for you? Okay, so I didn't even know I could do that. Okay, so 25. I don't even know how to fix this now.
You use the scroll wheel.
No, I'm using a Wacom tablet.
Oh.
I don't know what I did. I'm gonna stop the share. Share it again. I'm in PowerPoint. It must be the in PowerPoint.
Maybe.
And I'm in the view, like I'm showing the show. And I had my controls, now they're gone. My controls are gone. I can't like stop this. Let me see if I click it. No idea what I did. Okay, well, I'm gonna stop the share somehow. Am I sharing it all?
Just have your face.
Okay.
So normal.
You feel that exaggerate. Oh, it came back, but not shared. Okay. Is that better now?
It's sharing now.
Sharing. It's 25. Okay, let me screw this sucker up. 25.
That might have been it. Maybe you clicked on the thing and then clicked
Yeah.
again or something like that.
Yeah, it looked pretty, and I don't know how I fixed the problem last time. I really don't.
Well, I think what you're doing is on the bottom left, there's like those options.
Yeah, I can't get them to pop back up though. They would hover, when I hover over it down there, it usually would pop. Is there another way?
Yeah. I don't know.
They just had this. Okay, well, so let me go back and see if I can do it without the PowerPoints turned on. Okay, I was able to do it with blank touchscreen. All right, I'm gonna be careful. It was 25. That was, this is the answer, like up here is the answer for the problem. This is the expanded right here. That would be the expanded. So I don't want to confuse the two, but I was converting it over to the decimal for you as we were doing it. Okay, so converting binary to decimal. So we just did kind of that last one, doing, converted it over. So let's do some more. So convert a binary number to which is a base 2 to a decimal, which is base 10. We're going to write the binary number in expanded notation, admitting those where the bit is 0. And then it probably would have helped me out to actually omit the bits that were 0, so I wouldn't have made that mistake where I did 0 times 4 and got 4. I'd be more likely to not do it if I leave them off, because it's probably more intuitive to leave them off. Okay, so, and then we're going to add the resulting values like we did in that last example. So I've got the 1001.011, and let's take a look. So this is going to be 2 to the first, right? 2 to the first, 2 to the second, 2 to the third, 2 to the fourth. Then if we come to the other side of the binary point, this is not a decimal, it's a binary point, would be 2 to the 0, 2 to the 0, 2 to the 1, 2 to the 2, 2 to the 3. I screwed up my exponents. I'm trying to write tiny. 2 to this, right to the left of the decimal place is going to be 2 to the 0, 2 to the first, 2 to the second, 2 to the third. Then we'll have on the right side of the binary point, -1, 2 to the -2, 2 to the -3. So this most significant digit will be 1 times 2 to the third then plus, you know, the 0. I'm not going to write the 0. I'm not going to make that mistake again and make it, it wasn't a mistake. It just, it's, if you leave them off, it's going to be easier for you. So this 0, I'm going to leave, and then the 1 times 2 to the 0 plus this 0 times that is still going to be 0, so I'm going to skip that as well. So do 1 times 2 to the negative 2, and then 1 times 2 to the negative 3. And I need to add that between those two. I need it look like I'm multiplying them. Okay, I'll let you catch up. I'm going to make sure I didn't make any silly errors before we continue. Okay. All right, so then now we're converting. We'll take the 1 times 2 to the third. 2 to the third is 2 times 2 times 2 is 8. So that'll be 8 plus 2 to the 0 is 1. So 1 times 1 is 1. Plus, now you'll see we're going to have smaller numbers. 2 to the negative 2 is 1 over 2 squared, or a quarter. So 1 times a quarter is 0.25. Plus 1 times an eighth, 1 over 2, let's see, 1 over 2 cubed is 1 over 8. So we have 1 times an eighth. An eighth as a decimal is 0.125. So we'll add these. Well, 8 plus 1, that's 9. That's easy to add. And then 0.25 and 0.125 is 0.375. So 9.375 is this binary number converted to decimal. Questions on that? Okay, so make sure a couple things of caution. So you have your binary point. The place to the left is going to be 2 to the 0. Make sure you start with 0 there. 2 to the first will follow, and so forth. And then to the right of that binary point, we'll start with 2 to the negative 1, and so forth. More negative as you move to the right. Okay, so let's convert a decimal with base 10 to binary of base 2. So we're going to find the largest power of 2 that will divide into the number and put a 1 in this place. Subtract that power from the number and find the next largest power of 2 that divides the number and put a 1 in that place. And keep subtracting the decreasing powers of 2 until you get to the ones place. I don't mean it on purpose, but if you just read all that and understood, amazing. It's so, but it's when you just read all those words, it probably just all like jumbled together. So the best way to do it is just to jump right into an example, and that'll demonstrate it better than reading it in text. Who's done this before? Anyone convert decimals to binary? Dan, did you ever do this?
I did a little bit of it, not much.
Okay. So let's start with something relatively like manageable and small as a decimal number. So I have the decimal number, standard number that we would have is 59 with a base 10. And I'm going to convert it to the binary number, to its binary form. So the first thing I'll do, and I started with 2 nibbles, right? So a byte worth of spaces. So here's the first nibble, there's the second nibble, and this is going to be our, you know, the closest to the binary point. We'll be right here, that's our binary point. We have a whole number, so I don't really need the decimal, I mean the binary point. No. Okay, so I'm going to label my powers of 2. So this position here would be 2 to the 0 power. This one would be 2 to the first, 2 to the second, 2 to the third, and we'll jump 2 to the fourth, 2 to the fifth, 2 to the sixth, 2 to the seventh. Okay. Now, what are these numbers in decimal? You know, the decimal system. So it'd be 2 to the 0 power is 1. 2 to the first is 2 to the first is 2. 2 squared is 4. 2 cubed is 8. You get pretty quick with this after, you know, a little while. You can start counting by the powers of 2. So then you do another, you're just doubling. So 2 to the 4th will be another times 2, so that'd be 16. Then 2 to the 5th is going to be 16 times 2, which is 32. 2 to the 6th is 64, and 2 to the 7th is 128. So I have more than I need. And I know that because my number is 59. So I don't need to go really beyond 59. So what I'm going to do is put zeros here because the number is not above 59. So 64 and 128, I know I don't have one of those. So then I'm going to start subtracting the largest power that appears in that number. So the largest power I see is 2 to the 5th, so which is 32. So I'm going to subtract 32 from this number, from the number we started with. So I know one of those goes in, right? There's a 32 in there, so subtract it out, I'll get 27. So I've accounted for the 32. Now I'm going to add all these results, right? So I'm going to add this plus this plus this plus this, whatever I have. Now I look for the next largest power of 2 that goes into 27. Well, 16 goes in. There's a remainder, but let's do it goes in once. So put that there. 16, subtract, you have 11. 8 goes in. You can subtract 8 from 11. So I'll do that. You see what I'm doing? The pattern I'm getting here. So now you have 3. I'll stop for a second. Then I look at the next highest power of 2, but I can't subtract 4 from that. So I have to put a 0 there for the 4. And then the 2 I can, so I have a 2, I'll subtract that out, and I have a 1 left, so I can put a 1 here. I'll subtract the 1, I have 0, so we're done. Get down to 0. So that is the number 59 in binary. Let's try it again. With a little bit larger number, we'll do a 3-digit number. So we're going to convert the decimal integer 423 to its binary form. And you'll see I have 3 nibbles set up this time. And I'm going to start with, again, 2 to the 0 power, which is 1, 2 to the first power, which is 2, 2 to the second power, which is 4, 2 to the third power, which is 8. I'm going to start saying 2 to the whatever power and just start doubling. So it'll be 16, 32, 64, 128, 256, 512. Double this, be 1,024, and then last we'll have 2,048. Okay. All right, so I'm going to subtract out these numbers, these powers of 2. Once we can. We can't, this is a 0, this will be a 0, and this will be a 0. 512, 1,024, those aren't in 423. So the largest power of 2 would be this one here. So I can subtract, I'm starting with the 423 and subtract out the 256 because I'm going to use one of those, right? Let's do my arithmetic over here. So 7. I have 167. Well, 128, I can subtract that out, so I can use one of those. So subtract out 128. 9, 30. So I now have a 39. Well, 64, I can't subtract that from 39, so I'm going to put a 0 there. The next one I can subtract is 32. So 7 is a remainder, so I have one of those. So I have 16 and 8 that I can't subtract from 7, so putting zeros there. 4 is the next one I can subtract. And then a remainder of 3. So I'll subtract 2. Remainder of 1, so we'll use that 1. So now we're done. And that is the binary number for 423. Now you can see it as we use larger numbers, it's going to get pretty long for binary number. Okay, so method 1 works well if the given decimal number is relatively small, but becomes more difficult with larger decimal numbers. So the next slide is going to show us an alternative algorithmic method for converting decimal integers to binary. So let's talk about that, doing it a little easier when we have larger numbers. Okay, so again, I'm going to read the process, but it's going to be a lot easier to understand once we're actually doing the process. So to convert a decimal or a base 10 number to a binary, a base 2, we divide repeatedly by 2, keeping track of the remainder if it's 0 or 1. And the remainders form the binary number. Number 2, write the numbers such that the remainder at the top of the column appears at the rightmost of the binary number, and the last remainder is the most significant or the leftmost digit. And we're going to read our digits up. Okay, get right into the example. Converting the same number we did before, the other process, we're going to do it this process to see how it would turn out. It should give us the same exact answer. So we're converting 59 to the binary. So I'm going to take the number 59 and we start dividing by 2. And we're keeping track of remainders. So I'm going to do 59 divided by 2. And then I'm going to have a remainder column. So 59 divided by 2, well, 2 goes into that nicely 29 times, but that would be 58. So there's a remainder of 1. Now take this number 29 divided by 2. That's 14 with a remainder of 1. 14 times 2 is 28, so I have the remainder of 1. Now 14 divided by 2, that is even. So that'll go in nicely at 7. There's no remainder. Now I'm going to divide 7 by 2. I just keep doing this process till I get done. 7 divided by 2. Well, 2 goes into 7 3 times nicely with a remainder of 1. 3 divided by 2, 1, with a remainder of 1. And when you get to this point, I'll show you something in a second, but I'm going to take this 1 and divide it by 2 again, and you realize you can't do that, so that's 0 with a remainder of 1. So when you get down to 1, you can just bring that down here because you know you can't divide that by 2 again. So this 1 is really going to end up being the remainder, another line of remainder. Okay. So as we're writing this, these are now our bits. We start from the bottom. This is our most significant bit, and this is our least significant bit. So this is going to be near the binary point. So you can start up here and go down, but you can start here. I'm going to start from the bottom and go up. So it's going to be 1, 1, 1, 0, 1, 1. So writing it with the right spaces, there's like a, in groups of nibbles here, it would be 0, 0, 1, 1, 1, 0, 1, 1. Because the zeros, we only have 2 numbers on this side. So we would be fleshing it out by putting the 2. So we had groups of 4. And that's what we had before, I hope. Okay, the next one, I'm gonna have to write really tiny. We're gonna do that new method 2 again with this larger number, because if we did it with 8,375, that first method I showed you, oh my gosh, that would be long. So let's try it with this method, but it is gonna take up some space. So if you have extra paper, if you do not write small, you might wanna grab out, you know, a piece of paper or your notebook and write it down there. And I'm gonna do my very best to get it all on this slide. Okay, so we're gonna start by dividing 8,375 by 2. Keeping track of the remainder. So dividing by 2, you can use your calculator. It'll be 4187. And that has a remainder of 1. Now, only remainders we can have are 1 or 0, so that's a remainder of 1. Now we're going to take 4,187 divided by 2. And that's going to be 2,093. Remainder of 1 again. Now I'm taking 2,093 and dividing by 2. That's going to be 1,046 with a remainder of 1. I'm going to take the 1,046 divided by 2. That's an even number, so I won't have a remainder. This is going to be 523, so I don't have a remainder on this one. 523 divided by 2. $261. And a remainder of 1. $261 divided by 2. 130, remainder of 1. 130 divided by 2, and that goes nicely. That'll be 65. No remainder. 65 divided by 2. 32. 1 remainder. 32 divided by 2. 16. No remainder. Getting there. I'm getting there. 16 divided by 2. 8. No remainder. 8 divided by 2 is 4. No remainder. Okay, I can't do it there. I'm gonna have to come over here. 4 divided by 2 is 2. No remainder. 2 divided by 2 equals 1. No remainder. And then the 1 divided by 2, remember I had mentioned, that's going to be 0 with 1 remainder. So that basically comes down here. When you get down to 1, that does come down as the last remainder. Wow. Did anyone get it all down on the left without having to? Yeah, okay. So this is our most significant digit, least significant digit. So the binary point is going to be next to this one. You know, it's going to be this 1, 1, 0, you know, and that's going from the binary point, moving away from it. So grouping of 4, start here. I'll just draw lines for groups of 4, then it would be here. So if you want to go backwards, you could start with your binary point over here, and this would be next to it. So it'd be 1, 1, 1, 0, then 1, 1, 0, 1, 0, 0, 0, 0, 0, 1, 0, 0. Might have been, you know, you could think I have to put like a 0, 0 here, and so then you'd have this starting. I can't show you really. I'm trying to point with a mouse here. I'll try to get a laser cleaner. So this 0 corresponds to this one here. This is the next one here. So this is 1, 0 right here. This is 1, 1, 1, 0 going from the binary point 1, 1, 1, 0 in this direction here. So if you start from here, if you don't have 4 here after you've started grouping by 4 starting from the binary point, throw in some zeros for the placeholders there to flesh it out. So we had a nibble with 4. I wish I could point on my screen at the same time as the laser so you could see where my fingers are. Like this one corresponds to this. That one's there. It's there. You see what I mean? Okay. So that's your number. That's the number 8,375 in binary.
So anytime you have an answer that ends up being 1, like 2 divided by 2, it automatically goes to the binary side?
This right here, 2 divided by 2, that 1, is going to just drop down here as a 1.
Yeah.
Yep, at the end. Yep. That's the only thing we're going to have it is at the end. The 2 divided by 2 is only going to happen at the end. You wouldn't be able to go any further. So, yeah.
Okay.
So that's it for converting decimals to binary, and you'll have practice that is available. I don't know if I turned it on yet, but I'll turn it on right after class, and I'll show you. I'm going to bring you there after I finish up hexadecimals. So let's see here. Hexadecimal numbers, or we can refer to it as hex numbers, are obtained by grouping the bits in a binary number into sets of 4 nibbles and representing each set by a single number or letter. The base of a hexadecimal number is 16. So you'll see I have the decimal number 0, like the normal 0 that you would know. This is what it's like in binary. That's what it's like in hexadecimal. 1, the decimal number 1 in binary looks like this and looks like this in hexadecimal. 2 looks like this in binary, and so forth. So if I just looked at the decimal and hexadecimal, they look the same till 9, right? But decimals are base 10. So we've already used 10. We talked about 10 digits already. From 0 to 9, there's 10 digits. Hexadecimal uses the same 10 first digits, but then there's 16 total, so they have another 6. So that's A, B, C, D, E, F. So then they had to use other things, so now we're using letters for those. Okay. So now let's see how this plays out. And these are called hexets. I did want to mention these are hexets instead of digits. So these are bits. These right here are bits. These are hexets. Okay. So converting binary to hexadecimal. First thing we'll do is group the bits into sets of 4, starting at the binary point, adding zeros as needed to flesh out the groups. And then we'll rewrite each nibble or each group of 4 using the equivalent hex digit or hexet. All right, so we will start by grouping starting with our hex point right here, grouping them into nibbles, so groups of 4. So I'm going to draw my line here. There's only 2 here, so I'm going to flesh it out by putting 2 more zeros in front of it. Doesn't change the number, it just makes sure we have groups of 4. I'm going to do the same thing, find groups of 4 to the right of the decimal place. So that would be here. And I'd be putting another one in this group. So let's write it out into our nibbles. Let's group it. So I need 2 groups on this side of the hex point and 2 groups on that side. So we have 0, 0, 1, 0, 1, 1, 1, 1. Should not call it a hex point yet. It's a binary point because it's still a binary number. So this is the binary point. These are the nibbles. So let's take a look at this, and we are going to, we rewrote them into the nibble, so the group of 4, and now we're going to write the equivalent hex digit. Well, thinking about what this number represents, you can use the chart. If you look at 0010, what does this number represent? What would this be?
2.
2, right? So think of it, remember this is 2 to the 0 power, this is 2 to the first power, 2 to the second power, 2 to the third power. Now this, just in this nibble, not for the whole binary number, because this would be 2, 0, 2 is the first, second, third. But we're talking about in groups of 4. So if we're converting to hex, we're treating these separately. This is a group of 4, this is a group of 4, and not like treating this as number 5, 6, 7, and 8. You know what I'm saying? But you know, the 5th away from the decimal and the 6th. So this would have been, we have none of those. We have one of these, 1, 2 to the first, so we have a 2. That's this number in hex. This next group, again, 2 to the 0, 2 to the first, 2 to the second, 2 to the third. So this is going to be 8. Because you have one of those, 2 to the third is 8. So we have 8 plus 4 plus 2 plus 1. That's really tiny, huh? 8 plus 4 plus 2 plus 1 is what I have written down there. So you have 2 cubed, 2 to the second, 2 to the first, 2 to the 0. So when you add those together, it comes out to be 12, 14, 15. Well, in hex, 15 is not 15. Hex is, what's 15 in hex?
F.
F, right? You said F? That is correct. So how we get this, think about the first 10 digits are the same between decimal and hexadecimal. They're the same, 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. Then we get to 10. 10 is treated like A in hexadecimal. 11 is treated like B. 12 is treated like C. You might need to do this every time, little conversion after digit 9. You have to, you know, do 10 would be A. 15 is F. All right. Then we have the hex point right here. Now do this next group, next nibble. So this is 2 to the 0 power. That's 1. So we do have that. Plus we have 2 to the first power, which is 2. Then these are zeros, so we don't worry about those. So this is just a 3. And 3 means 3 in hex. And here, 2 to the 0, we don't need to worry about. We have 2 to the first, we'll have 2 to the second, and 2 to the third. So this is 8, 4, and 1. So we'd have 8 plus 4 plus 1. That's 13. 13 is a D. Nope. What did I do? 8. See what I did here? I treated 2 to the first as 1. What's 2 to the first?
2.
So I have 14, which is E. This looks really spaced out, so our final answer would be 2F.3E. That would be our hexadecimal. Okay, so going from, we don't have much more, but I do want to make sure we practice the rest of these. So converting from hexadecimal, so the base 16 to binary or base 2, we're going to convert each hex digit into its equivalent binary nibble. group of 4 bits. So the hex number 7B2.D0E, we're going to put that into binary. Each one of these hexets is referred to a whole nibble, all 4. So I'm going to spread this out. I'm going to make this, I'm going to write out this hex number pretty spread out, so then I have room to do the nibbles.
So in this case, would you use method 2 to get the numbers?
So method 2, we're kind of going backwards where we were saying, not method 2 the way I have it labeled for the converting decimals to binary, where we're dividing. We're not going to do that. Well, we kind of, I'm going to say quasi. I'll say quasi. It's a little bit different than method 1 or method 2 in this way. It's only one way to do this that I'm showing you. So I don't really have 2. So the nibble is, again, a group of 4, right? So it's a group of 4, and this is referring to 2 to the 0, which would be 1, 2 to the first, which would be 2, 2 to the second, which would be 4. Oh. Okay. And then 2 to the third, which would have been 8. So if I have the number 7, so when you're saying like divide by 2 with the remainder kind of thing, I think that's why I'm saying quasi, because it's like that. Yeah, I'm not going to say no, but it's, so you're not going to have a number here. So I'm going to put a 0, doing them down here. I'm going to do the little 4s underneath the 7. We do have a 4 that goes in one time with a remainder of 3, right? So 7 divided by 2, which you said 3, remainder of 1. Then we're going to say 3 divided by 2, that's 1 with a remainder of 1. And then when we get down to that 1 divided by 2, we don't write anymore. We can just bring that down. So we would have that extra 1. So the 7 would be 0, 1, 1, 1. So the quasi part was what I was saying. You're just going to take the remainder and kind of for each piece, you could kind of do that method too. Okay, what does B refer to as a decimal digit? Which you don't really have, I guess, a decimal digit, but the decimal number.
Would be probably 12, right? Though.
I think
if
it's
you're using
11.
That.
Because 10 is A.
Oh yeah, you're right. Yeah.
So it's an 11. So just put a little reminder that it's an 11. I'm afraid to put the ones there because it almost looks like 1, 1, but it's 11. So 11. So take 11 and divide it by 8. It's going to happen. It's going to go in one time. And then you have 3. So not a 4. You'll have a 2, and you'll have a 1. So 11 divided by 2. Divided by, sorry, 6. I'll do that. Okay. 2. In binary, you probably already memorized it, 0, 0, 1, 0. You only have it here, so you only need to put a digit 1 here. So this would be 0, 0, 1, and a 0. Then we have our binary point that we're putting in there. It matches up with our hex point. The D refers to, well, A we said was 10, B would be 11, C would be 12, D would be 13. So we have an 8 in there, right? So we have an 8, remainder of 5. So we'd also have a 4 in there. So 8, 4, and a 1. 12, no, yeah, 13. Yep, 12, 13. You're just basically adding these groups. Like, how can you get these to add up? So we'd have 0, 1. And then 0, don't overthink it. It's just going to be a group of 4 zeros. And then E is 14. So how do you get 14 out of all this? Well, 8 plus 4 plus 2, that would be 14. So you have a 1, 1, 1, 0 for the E. It might be easier instead of doing this method too, as you're saying, but like say you said 4 plus 2 plus 1 is 7. So then you could put, you know, they'd have a 0, 1, 1, 1 in those positions. You need an 11. So find what digits add to 11. That was going to be 8, 2, and 1, and so forth. Okay, so next, hexadecimal. Hexadecimal. Oh, I went too far. Hexadecimal 4C point F. You know, every time I see these, I feel like they look like Canadian license plates, but sometimes when they're grouped, but. Okay, write the hex number in expanded notation using powers of 16 and then add the resulting values. So converting from hex to decimal. So I'm going to write 4C point F. Now, thinking about the base is 16 in hexadecimal. The base is 16. So next to the point, the hexadecimal point here, the hex point, the base 16, this is going to be base 16 to the 0 power right next to it on the left side. And then it's going to be 16 to the first power, 16 to the second power, and so forth. To the right of the hex point, this would be 16 to the negative 1 power. So we're going to write this in expanded notation. So this is going to be 4 times 16 to the first power plus, well, what is C? A was 10, B is 11, C is 12. So we're going to have 12 times 16 to the 0 power. And then plus, over here, we have to find out what F is. Well, F is 15. This is very, and there we go, 15. So it'd be 15 times 16 to the negative 1 power. Now we can add these. We have to do the multiplying, we can add them. So 4 times 16 is 64. Plus 16 to the 0 is, that's 1. So it's going to be 12 times 1, which is going to be 12. And then this is going to be 15 times 16 to the first negative 1 power, which means 1 over 16 to the first power in the denominator. So 15 times 1 over 16 is 15 sixteenths. So it's going to be plus 15 over 16. So adding, you can use your calculator. I want it as a decimal. So this is going to be 76. And then 15 sixteenths as a decimal is 0.9375. And that would be the hex number converted to decimal. Okay, so just like you saw in method 2 when we were converting a number to binary, we'll do this when we're converting a decimal to hexadecimal. We'll be doing a very similar, but instead of dividing by 2, we're going to be dividing by 16. So divide repeatedly by 16 until the quotient is 0 and keep track of your remainders. So let's keep doing that. And you can read that information a little slower, but it's best to get into the actual practice of it, and then you can go back and read it and see that it makes sense. So 83,759 we're converting to hexadecimal. So start with the 83759. We're dividing by 16 and keeping track of the remainders. This is where a calculator is probably going to be helpful. Not going to lie. $16 goes in 83,759 15 times. Oh, no, I'm lying. My rate of remainder. So 5,234 times, right? With a remainder of 15. How do you find that remainder? Take this number times 16, subtract that from this here. So in my calculator, I took 8.3. Can you see my calculator? Am I sharing that properly?
Mm-hmm.
Okay. Divided by 16, I'm getting, oh, I'm in scientific notation. I need to go back, or engineering, sorry, back. Okay, so this was, it went that many times, and it has this as my remainder. So I can take the 5,2, there's a few ways you can do this. 5,234 times 16, and I can subtract. I know that I'm subtracting, I'm gonna get a negative. I don't want a negative, but it helps me not have to use some, you know, to do a lot of subtraction here. So it'd be 15 as my remainder. Just negate that it's, just forget that it's negative. The other way you can do it is take the 8,3,759 divided by 16. I'll start there again. We have this number. So when in this many times, so you can take this decimal 0.9375 part and multiply it by 16, and it should tell you it's 15. That might be faster and maybe less confusing. Either one of those ways will do it. So that's a remainder of 15. So now we've got to take the 5,234 divided by 16, and you get 327. The remainder here, when you get it, let me know the remainder.
Two.
I have 2. Then if I take 327 divided by 16, what's my number here?
It's 20.
20, and the remainder of 7.
Yep.
Okay. So then we're going to take 20 divided by 16. This goes a little faster because the 16 divided by 16 is faster than dividing by 2 when we're doing binary. So 20 divided by 16 is 1 with a remainder of 4. And that one I can do without the calculator. And then when we're down to that 1, remember, you can just bring that down as your remainder, because 1 divided by 16 is not going to get us anywhere. That's going to be 0, and that's our remainder for that. So you can just not do this part, this last line, because that 1 is going to come down. Now, our goal was not, this is to convert it to hexadecimal. So we need to set up another list here and convert what 15 is in hex. What's 15 in hex?
F.
F. 2.
Normal 2.
Yeah, 7 is 7. 4 is 4, and 1 is 1. So this is our most significant digit. So this will be most to the left. And then this would be our least significant digit. That'll be most to the right. This is a whole number, so I don't have any decimal place. I don't have a hex point either. So it's going to be 1472F. That's our answer. You made it. You made it a whole hour and 50 minutes, no break. If I could, like, give you candy, I would. I can't really do that right here. You know, give you some. But you need to go have a lunch.
Yeah, I think there's like a screen or something like that.
A screen for food?
Yeah, between us.
Yeah. Oh, yeah, between us. Yeah, there's. So I can't. So
Yeah.
I wish I could, because you deserve it after that. I do want to show you one more thing so that we're familiar with the homework and all that. So you'll see I have the homework. I'll show you what it looks like this, okay? You'll be able to access it. You can do it right away if you're feeling like, whoa, I got to do this right now, practice. And I'm going to have you scan it in, and I'm going to grade it by hand. It's due Saturday, by Saturday. So the sooner the better, because you don't want to forget all this fun stuff. Feel free, like you have contact information with your classmates, you're welcome to reach out to them. If you wanted to check it, you can send it to me to have me check it. That's fine. And I also want to show you one more thing. I just want to share again. Share that one. Okay, so in here, oh, it probably kicked me out. Oh, you might be able to let me show you. See, I still have your calendar up. This is really small. Maybe if I can learn my Zoom trick that I learned in the other one, I could make it bigger. Here we go. So if your schedule for this week. So we only did 2 of the 3 things. Thank goodness, right? We don't have time for that last one. The section 1.5 and then the binary and hex conversions, those are graded assignments. The 1.5 is in my math lab. The hex conversion is going to be attached. I will make sure you can see that in about, as soon as we get off. And that is still due Saturday, and there's going to be a Dropbox. Just scan it in. The section 1.6, I don't want to get too far behind, so I'm going to videotape myself doing that and then I'm going to upload that video by this evening. And I want you to watch it before Tuesday. I don't want the homework done by Tuesday or anything. I just want you to watch the video by Tuesday and fill out the guided notes. So that when we come together on Tuesday, we're going to start with section 1.7. I'll go over any questions you have on 1.6, but that homework won't be due until Thursday of next week for 1.6. So you have some time for that, but I just want you to watch the video ahead of time so I can start with you at 1.7 on Tuesday. I don't want to start at 1.6. I want to start at 1.7 so we don't get ourselves behind. So you can watch it whenever you want to. Any questions on that? Okay, great. Please go get some lunch. Enjoy the rest of your day and have a great weekend. It's Labor Day, right? So we have classes Monday. Not us, not our class, but if you have classes on Mondays, we still have our classes Monday. Okay, see you guys later.
All right. Have a good day.
Bye.